Planning a software project gives us concrete administrative boundaries. We calculate the budget, we set the timeline, and we determine exactly how many developers need to be hired. But establishing the parameters of what we are building completely sidesteps the technical reality of how those developers will actually construct the system. This diagram maps a standard software development timeline. We gather requirements, then tend to jump across this blank gap directly into writing code. That gap is dangerous. Abstract needs do not automatically translate into machine instructions. To cross this void, we insert software design. Not a single line of code should be written until this intermediate translation layer is complete. Think about the process of constructing a physical building. A crew of workers cannot just arrive at an empty lot and start laying bricks. They require an architect's blueprint, a schematic detailing the exact layout of rooms, the placement of doors, and the routing of electrical wiring. Software design is this exact blueprinting process, applied to digital construction. Instead of load-bearing walls and plumbing, a software blueprint defines the overarching system structure. It dictates the distinct modules, maps the flow of data, and outlines the user interfaces. It takes a list of abstract business requirements and converts them into a concrete, executable technical plan. Imagine a scenario where 10 programmers are hired to build a large application and instructed to begin coding simultaneously with no unified design document. Everyone starts writing in their individual style. Without a plan, the separate pieces of software cannot communicate. Data gets duplicated across the system. As these conflicting pieces of logic crash into each other, bugs multiply. Now see what happens with a central design document. The blueprint establishes strict module boundaries. Every developer knows exactly which component they are responsible for, what the shared database schema looks like, and exactly how their module needs to format data to send it to the next developer's component. Design intercepts uncoordinated execution and replaces it with structured modularity. Enterprise-level software systems contain thousands of interdependent variables, making them too complex for a single human mind to understand as a single unit. The first objective of software design is to reduce that complexity by dividing the massive whole into smaller, highly focused chunks. The second objective is creating reusable components. By standardizing these chunks, features like a login screen or a reporting engine can be lifted and deployed into completely different future projects. The third objective is ensuring flexibility. A structured system isolates its features, so when a client asks for an update, like adding a dark mode, developers can modify the user interface without accidentally breaking the core logic. To memorize the characteristics of a robust architecture, engineers use the mnemonic design. D stands for divide into modules, and E means the architecture must remain easy to understand. S dictates the system should be secure and simple, while I provides a clear implementation plan. G represents the governing architecture, ensuring efficiency under heavy loads, while N reminds us this plan is needed before code is ever typed. When a system possesses these traits, future modifications are inexpensive and new features integrate safely. Creating this blueprint happens across two distinct planes of abstraction, starting with high-level design, or HLD. Think of high-level design as the helicopter view. From this altitude, you map out major districts and connecting highways, completely ignoring individual streetlights or pedestrians. To map this out practically, we can draft the architecture for a hypothetical food delivery application. The first step in HLD is identifying the macro modules. For our food app, we define 5 primary blocks: the customer, the restaurant, delivery, payment, and admin. The second step is defining how these macro modules communicate. We map out the path data takes from the customer making a request to the restaurant receiving it. Finally, we assign overarching database structures and dictate the architectural standards the entire system will adhere to. High-level design establishes the structural boundaries and integration points before a single piece of specific application logic is formulated. Once the macro architecture is set, we move to low-level design, or LLD. This is the lens view. To execute LLD, we abandon the overarching map and inspect the interior of one specific module, our payment gateway. We map the precise logic, drawing a flowchart moving sequentially from input validation to card authentication. Next, we start drafting the pseudocode. We outline the mathematical algorithms and internal functions required to actually execute that flowchart. Then we define the specific database tables and internal variables those functions will manipulate. This granular level of detail is entirely dependent on the step before it. Low-level design can only be drafted after the high-level design establishes what the module is supposed to achieve and what external data it will receive. Low-level design provides the exact programmable instructions a developer requires to finally sit down and begin writing code. Software design bridges the abstract concept of what needs to be built and the executable reality of how a machine operates, stepping from the macro architecture of HLD into the micro execution of LLD. This chart shows the financial stakes of the design phase. It tracks the cost of fixing a software defect across 4 chronological phases: design, coding, testing, and deployment. If a foundational error in the architecture is missed early and only discovered after deployment, the capital and time required to fix the system rises exponentially. A correctly designed system sidesteps these penalties by guaranteeing a flawless, bug-free data flow between its components. This presents the next logical question for a software engineer. Once we draft our HLD and LLD modules, how do we actually measure if they are structurally sound? We evaluate design quality using 2 critical engineering metrics: cohesion and coupling. Cohesion measures the internal strength and operational focus within a single module. Coupling measures the level of external dependency and data reliance between different modules. Mastering the balance of these 2 metrics determines whether a system can scale sustainably or if it will eventually buckle under the weight of its own internal dependencies. We will calculate exactly how to optimize them in the next lesson.